Welcome to the Insightful Professor. Today we continue our examination of user-defined types in the relational world. We'll continue where we left off with our discussion of structure and identity. We'll be looking at column objects and row objects, specifically how these things are declared and some of their characteristics, associated metadata. Then we'll look at how to access these objects stored in a relational framework using SQL. Once we've defined our user-defined type, we've effectively added a brand new data type to the database. We can then use that data type to define a column within a relational table. Relational tables can store objects along with other table data. Note again that the table or relation remains the primary structure in the object-relational system. What we have accomplished to this point is to simply add a new data type to the system. We can now go beyond the basic built-in data types provided by the vendor. In our case, the Oracle database. When a user-defined type is used in this way, the object that's instantiated is referred to as a column object. Here, our simple example does not yet reveal how much we can accomplish, but it does serve to present the fundamental framework provided for our task. Note that the relational table has been defined with constraints on its columns or attributes. Employee number is the primary key, therefore it's unique. Name is defined as having a not null constraint. As we move through our example, we will more closely examine how constraints can be defined on a column object. Using the describe command, we can access some of the metadata about the table. The structure that is revealed through this command shows in our example that the object type used for a column object appears as the data type of that column. Rather than use the describe command, we could construct our own query against UserTab Columns. This table describes the columns of all tables owned by the current user. This is not something new to support object functionality. So UserTab Columns is not specifically associated with user-defined types. This table describes the columns of all tables. Our interest lies in how the vendor has incorporated the information for object types, something that was not part of the original relational product. Once a user-defined type has been created, it is available to the database as a data type for a table's column, just like the built-in data types that were provided by the vendor. The metadata regarding the table and its columns that is returned by using the describe command is actually obtained from UserTab Columns, part of Oracle's data dictionary. What we want to bring to your attention here is this is only a subset of the columns within UserTab Columns. If you describe UserTab Columns, there are many additional columns within this table, but we want to focus on just a few of these. Column name is the name of the column within the table. Data type refers to the data type of the column. This can be either a built-in data type or a user-defined data type. Data type owner applies only to user-defined data types, because a user-defined data type is actually something created within the database. You create tables, you create indexes, you create views. You can also create a user-defined type, create a type. So there's a concept of ownership. So the type is owned by a user or schema. This is an additional column that was not really relevant back in the days when Oracle did not support user-defined types, prior to version 8. We'll need to examine some of the other columns as we define new types to see what values are reflected in these columns. Note that some of the columns not shown here contain statistics used by the optimizer. We need to address the issue of how statistics will be collected and how they will be recorded in the data dictionary. This is part of what Stonebreaker referred to as registering the new types with the system. Let's look at a query against UserTab Columns. Here we're selecting the name of the column, the data type, and the data type owner. And again, this will be populated only if it's a user-defined type. The data length. We select this for the employee table that we created, which contains a column called home address, which is of the user-defined type address, which resides in Mo's schema. Let's bring a column object into existence. To populate a column object, or say a column in a table that can hold an object, we have to invoke the constructor, or what Oracle refers to as the constructor method. The constructor is created automatically by the system when the object type is defined if we do not provide our own definition of a constructor. This default constructor is referred to as an attribute value constructor. It is not user modifiable. It has the same name as the object type. It's always a function that will return the object that has been instantiated. Remember that methods could be functions or procedures, but the constructor is a function. The arguments to this attribute value constructor correspond to the attributes of the object type. An attribute value constructor requires a value for each attribute of the type. If it's a type that you're not familiar with, the SQL+ describe command allows us to describe the type and reveals information about the attributes. Then we could make a valid call to the attribute value constructor. Now, when an object type is used as a column object, the entire object is considered a single attribute of the table. The call to the constructor method, together with the attribute values, is provided as a single value to the SQL insert statement when we're inserting a row into the table that will hold the column object. We've created the UDT called address, and it has 4 attributes. Here we see a call to the address constructor. Optionally, when we invoke the constructor, we can supply the keyword new to express the notion that we're instantiating a new object instance. But new is optional. After applying the inserts, we can query the table. After applying the inserts, we can query the employee table, and what we see in the home address column is something a bit odd. Instead of showing us the street value, the city, the state, the zip code, it effectively shows us the call to the constructor with the attribute values. So one of the supposed benefits of extending a relational database management system to support objects is the continued use of SQL. This is the same language and set of operators that we used to work with traditional relational data. You apply this same language to objects. As we shall see, preserving SQL as the DML does not necessarily mean that the relative ease of working with relational data is also preserved, because now we're working with complex structured data. Some of the constructions, that is the syntax, might be a bit awkward or cumbersome, to say the least. Suppose we wanted to drill into the column object and extract individual attribute values. Remember, at this point, we have no methods defined, so we have no accessor functions or getters. But because this is a hybrid environment using relational database, we could grab the object and then drill into the object to extract the attribute values. In order to do this, we need a correlation variable. Observe in the from clause here, after the name of the table, which contains the column object, we introduce an arbitrary table alias or correlation variable. We call it P. This is a requirement. P is used to qualify the column that contains the object value, p.homeAddress. Then we express a path expression by using a dot operator to go a step further and extract the value of an individual attribute of this column object, p.homeAddress.street, p.homeAddress.city. So the dot notation is used to identify the attribute of the object qualified by the correlation variable. So note that home address is the name of the column, not the name of the data type. Consider for a moment the requirement of a correlation variable in the previous query. This query has nothing to do with objects, but it reminds you of the role of a correlation variable or table alias. Here we're selecting from the course table where the lab fee is greater than some value. There's a subquery. The subquery is selecting from the staff table the highest salary of any staff member where the department ID of the staff member is equal to the department ID of the course. This is a correlated subquery. Question is, to which table does C department belong? If you describe the staff table, it's not a column in the staff table. It's a column in the course table. We are actually making a refer back from the subquery to the main query. It's kind of implied here. There's no explicit correlation variable. Question is, what would happen if a column named C department was actually added to the staff table? If we altered the structure of the staff table and created a new column called C department, there would be no refer back to the course table. The idea here is the system said I couldn't find C department in the staff table. Let me go back to the course table. I find it there, and this is what makes the correlation back to the course table. But if there's no need to go back, if the reference to C department can be established within the staff table alone, then we're staying strictly within the staff table and never go back to the course table. It's not a correlated subquery. It's just a conventional or traditional subquery, which is sometimes called non-correlated. The point is that for this query, we want the system to go back to the course table to provide the context for executing the subquery. To ensure that that's done, we could have said select max e-salary from staff where DEPT is equal to course.cDEPT and force the association back to the other table. The system resolves the reference to a column according to a process called the inner capture rule or inner capture. The use of a correlation variable to qualify columns avoids a possible misinterpretation of column ownership. That's what could happen in the query that we just showed you involving course and staff. To ensure that such a misinterpretation does not occur with respect to the methods or attributes of an object, Oracle requires the use of a correlation variable. So in our query against course and staff, the correlation variable was optional. We didn't have to have one there. But whenever we use objects, we're forced or obligated to use a correlation variable. This requirement is called the capture avoidance rule. Remember that I had said SQL is not quite as simple and straightforward working with objects in a relational framework. This is one of those situations. The output of a query using a correlation variable to extract an attribute of a column object closely resembles the output of a query against a standard relational table. Of course, the column headings show this dot operator. home address.street, home address.city, but effectively we've simplified the result just as if it was something like select asterisk from a standard relational table. Columns produced by a query could be renamed, just as we can do with columns involving standard relational tables. This would clean things up a bit. So instead of home address.street, we could simply have it as street. Home address.city, we could simply have the column presented as city. Then it would look just like the output of a query against a standard relational table. We can also perform data manipulation operations such as update and delete. A column object can be updated by replacing an existing object with an entirely new object created by invoking the constructor. Remember that home address is the name of the column in our relational table, which contains the object. So here we're invoking the constructor to create a new object and effectively overlaying the existing object with this newly instantiated object. Then when we query the employee table, employee number 222 has a different value for its home address than it had previously. So changes made to objects stored in the database can also be committed and rolled back. That is, these changes are part of a database transaction. The Oracle database system treats complex data associated with a user-defined type just like data of some built-in type. This means that the changes are considered tentative until the transaction completes. Commit and rollback can be used with changes involving data of a user-defined type to either undo the changes in the case of rollback or to have the changes persist in the case of commit. Although this example invokes the constructor to instantiate a new object instance, it's possible to assign an existing object instance to a column that holds a column object. It's also possible to take an attribute of an existing column object and update only that attribute, preserving effectively the existing object. The object must be accessed using a correlation variable. In this example, we're updating the employee table, and we arbitrarily chose P as the correlation variable. We then use P to qualify our reference to home address, specifically the city attribute, by using a path expression, p.homeaddress.city, and set that to a specific value of an appropriate data type. Here it's a character string. And we localize the effect only to the row where the employee number is 222. If we query the employee table after the update, sure enough, we see the modification that employee 222, Larry, now lives in Rocky Hill. A row that contains a column object can also be deleted from a table. This can be accomplished by specifying a predicate that references a scalar column of the relational table or an attribute of the column object. This second approach requires the use of a correlation variable. Note that given the current content of the values within the employee table, these two delete operations will accomplish the same thing. Employee number is the primary key, a scalar column, and we specify the value of that key targeting a single row. Alternatively, we can go into the employee table, grab hold of the object, the column object stored in the home address, look at its city attribute, and assuming that employee 222 is the only employee who resides in the city of Wethersfield, we'll delete the same row as if we had specified employee number 222. In general, the use of an object type as an attribute of a relational table really isn't any different from using a built-in type. When real-world objects represented by rows in a table cease to exist, the rows that represent these objects can be removed from the table. It's also possible to remove the entire table containing objects from the database. This is no different than removing a conventional relational table that does not store any objects. We simply drop the table. Thus far in our example, we have simply extended a relational database management system to support user-defined types, revealing very little difference from the built-in types provided by our vendor. But now we're going to investigate something a little bit different. Objects can be stored in two types of tables. Relational tables, where objects are stored with other table data. The second type of table is an object table. These tables store only objects. In an object table, each row represents an object, which is referred to as a row object. A table of objects is called an object table. However, the ANSI SQL 1999 standard refers to this as a typed table. Each instance of an object type contained in an object table is called a row object. The structure of an object table appears to resemble the structure of a standard relational table. Each attribute of the object type becomes a column of the table. SQL references to the attributes are not qualified as they are with a column object. The syntax for creating an object table is more complex because the table resembles a relational table and therefore supports the same integrity constraints. However, it contains objects. Here's the basic syntax with a simple example. Create table, and we give a name to the table of, and then we specify the object type. Each row will be an object instance of that type. Using our address type, we can create a table, and here we call that table addresses, which is effectively a table of address objects. The structure of an object table can be examined using standard relational database facilities. The SQL plus describe command can be used to describe addresses, which is a typed table or object table. Each row represents an instance of the object type. Looking at this description, it looks just like the table had been created with this create table statement, which would make it a traditional relational table, not an object table. But what's the difference? Internally, each row is an instance of an object type, and it has something that the relational table would not have. Each row can be accessed or referenced through a type of object identifier. Oracle Database makes a clear distinction between a traditional relational table and a table of objects that appears to be a relational table. This distinction is evident when we look at the system catalog. Information about a standard relational table is exposed through user tables. Information about an object table is revealed through user object tables. Because these are both tables, Oracle consolidates this metadata through another view, user all tables, which reveals information about all of the tables in the user's schema, both relational and object tables. Note we're viewing the metadata from the perspective of an individual user. So we're looking at the user views. Keep in mind that the Oracle metadata consists of three levels. There are user views, there are all views, and there's also a set of views for DBA. User reveals only those database objects that pertain to the individual user. All includes those objects plus items owned by other users who are permitting the current user access. And DBA looks effectively overall at the system level. Descriptions of the columns for either a relational or object table can be found in UserTab Columns. Remember that the object table presents its data to us as rows, but the table is really a collection of objects. The difference between an object table and a relational table is that each object in an object table has an object identifier, or OID. Object identifiers are not part of a conventional relational table. There are many columns in user object tables. We're providing only a few to give you a feel for the content of this particular data dictionary view. We have the table name for the object table. Then, because this is a collection of objects, object ID type is a column that applies to object tables. This indicates whether the object identifier is user-defined or system-generated. We'll have more to say about that in a future video. Table type owner is the owner of the type of the table. This is the schema in which the user-defined type resides. Table type is the type of the table. Another interesting enhancement to Oracle database that relates to object functionality is something called a collection. A collection can take a couple forms. It could be a variable element array, or it could be a nested table. This column called nested indicates whether the table is a nested table. Again, we'll address details of this concept in a future video. Some of the relevant columns for user all tables would be the table name, the object ID type, the table type owner, if it's an object table, the table type, again, if it's an object table, and whether the table is nested. A query against user object tables is presented here. We'll go into the database and try a few queries and kind of explore some of the metadata. First, we'll create the object table, a table of address. Let's review the structure of the address type. We have 4 attributes within a type. Now, let's review the structure of this table, the object table. It looks identical. That's because each row within this table will be an instance of the object type. Let's go ahead and examine some of the metadata we discussed. Going against user object tables, we'll identify the name of any object table that we have, the owner of the object type, the name of that type, and also information about the OID, or object identifier. And we see that we have one such table, addresses. It's within the schema of Mo, and Mo happens to be the schema that owns the object type, address, and it's a system-generated object identifier. Let's look at the relational tables in this schema. We have employee, a table we've been working with as we explored column objects. And finally, let's examine all of the tables within this schema. This will give us a list of object tables and relational tables. We've included not only the name of the table in our query, but a request to see the table type. Notice that for addresses, the table type is the object type address. For employee, there is no table type. It doesn't apply because this is a relational table. Let's go ahead and instantiate a row object. We'll insert an object into our object table. So we insert into addresses, and in the values clause, it looks as though we're dealing with a traditional relational table. We're providing one value for each of the columns which we believe to exist within a table, but in reality, we're providing one value for each of the attributes of an address object type. It works fine. Alternatively, we could use the address constructor, which makes sense because we're constructing an object. In this case, it becomes a little clearer that we're actually working with an object table. In the first insert, we could very well be working with a relational table. We can't really tell the difference. Remember, this is not a pure object-oriented database system. It's object-relational, kind of a hybrid system. We run this insert, and it works just as well. Let's look at what we have in addresses. We have two rows inserted, actually two objects inserted into the table. Each one has a distinct object identifier. In fact, if we were to take this second example and make a modification to it, where what we do is eliminate the explicit invocation of the constructor and do the insert in the same way we did our first insert, we're creating a brand new object. If we then look at what's in the addresses table, we see two rows that appear to be identical. There are actually two distinct objects within the table. They each have their own object identifier. They have the same values for the attributes, but they are separate objects. This is similar to having only a subset of real-world attributes to describe some individual. For example, consider the attributes of first name, last name, height, and foot size. It's possible that two distinct people could have the same values for these attributes, but they are still two individuals, two different people. If these are the only attributes available, then the two individuals cannot be distinguished. In this example, in this object relational framework, the object identifier, or OID, created for each object will be different. It is not dependent upon the values of the attributes. An important difference between column objects and row objects can be seen when we access data within a table. Let's first consider a query against our object table called addresses. We're retrieving entire rows, but in reality, we're retrieving objects. Now, let's suppose we want to pull some attributes. Don't look at the entire object. Then we could do something like select city, state from addresses. And notice this works fine. There's no need for a correlation variable when working with row objects. We also can change the value of an attribute using the SQL update statement. Let's suppose we wanted to change the city for the objects where the street name is Main Street. Our predicate in the where clause simply says street equals Main Street. Setting the value of city, we simply say set city equal to Wethersfield. And we've updated two rows. Let's examine the table. And we see that now everyone lives in Wethersfield. Let's recap our demonstration. We looked at instantiating a row object by using the SQL insert statement. We said that we could insert a row object into an object table simply by providing the values for each of the columns, hence each of the attributes of the object to be instantiated. We also indicated that invoking the constructor explicitly was not that it was not necessary to explicitly invoke the constructor. Data retrieval, we indicated, is performed on an object table or can be performed on an object. Data retrieval can be performed on an object table just as if we had scalar values in a traditional relational table. Select asterisk from addresses returned an entire row, and notice this is quite different than when we extracted a column object, where we saw the object was returned to us kind of intact. There was actually an indication of the constructor to say that this is an object, and then the attribute values. We also can access individual attributes of the row objects that are stored in our table without the need to use a correlation variable. The update statement can be used making the object table, again, look very similar to a relational table. We can refer to the attributes in the set clause and in the where clause, and again, there's no need for path expressions or correlation variables. And finally, performing delete, we can remove individual object instances from the object table, just as though we're removing a row from a traditional relational table. Simply formulate a predicate which makes a reference to an attribute of the object to be deleted. So summarizing what we've talked about here, with this example of a user-defined data type, or an object type, we presented an overview of the framework through which objects are supported within Oracle Database. The discussion touched upon the following points. The create type statement is used to define a user-defined type or an object type. When an object is stored in the database, we have two options. We store it within a table, so we can store it within a traditional relational table, putting it within a column of the table. We create a column object. Alternatively, we can make this table a typed table or an object table, in which case we create an entire row, which is really an instance of the object type. We examined metadata for the user-defined types and saw how that was stored and became accessible in the data dictionary or system catalog. We indicated that objects can be manipulated through standard SQL, and also the constructor method that we were invoking was system-defined. We'll look in a future video at how to write our own constructor. So I hope you found this video informative and beneficial to you in understanding object-relational database, how we can store and work with objects within a relational framework. Again, we're using Oracle Database as an example to illustrate the concepts, but these concepts have been extended to other databases because they're part of the ANSI SQL 1999 standard. Once again, thanks for watching.